Hey there, my name is David Liu, and I'll be presenting on the third lab of Intro Physics 1 at Georgia Tech titled Black Hole. The purpose of this lab was to use fundamental physics principles to create a computational model. Using a unique star trajectory tied to our school email address with a pseudo-random number generator, we would simulate the interaction of a black hole system with Web VPython. The lab was split into two parts, determining the mass of a black hole by proxy of the star's trajectory around the black hole, and using the computational model to find the initial velocity of a spaceship that would need to get close to the black hole without crashing into it. The main results are previewed here. The position update formula and velocity update formula were of importance as they allowed us to predict what the change in position over time and velocity would be. They're derived from the momentum principle, which states that the change in momentum over the change in time is known to be equal to the net force, related through Newton's second law. The universal law of gravitation was used to determine the attractive gravitational force, assumed to be the only force acting in these scenarios, fell between the star and the black hole in part 1, and the planet, black hole, and spaceship in part 2. The net force would be decomposed into its constituents. The parallel component, the p hat, is parallel to the direction of motion and describes speeding up or slowing down, while the perpendicular component describes curving motion, the magnitude of momentum times velocity, or mv squared, divided by the radius of the kissing or turning circle. This would be multiplied by n hat, which points towards that circle's center. The starter code that we used was very similar to that used in previous labs. However, instead of predicting future motion from a net force, the motion was instead used to find delta p over delta t, with the net force acting on the system. The while loop proceeded until the condition was false and advanced with delta t in each iteration. The initial conditions were entered, total elapsed time between data points, or 1 day in seconds, the universal gravitational constant, time for the first data point, and the mass of the star. The lists and brackets shown here refer to IDX, or the variable used to index in the list, or the data in an ordered fashion. Each of the corresponding formulas are shown to the right of the Python script as translations. The parallel component of the net force was assumed to be equal to the magnitude of the initial momentum subtracted from the magnitude of the final momentum, divided by the change in time multiplied by p hat. Because we didn't know the radius of the turning circle, without deriving it, we could simply use vector subtraction to find the perpendicular component. Also included in the program was a code that would draw arrows showing fnet, fnet parallel, and fnet perpendicular to assist with visualization. And shown here are the results. The magnitudes of fnet, or gravity acting upon the star, fnet parallel, are shown, and the star's orbit was depicted by the green ellipse. An increase in speed and the size of the force arrows was seen as the star got closer to the black hole. The mass of it was ultimately found to be 1.29 times 10 to the 34th kilograms. Much like in part 1, the program utilized iteration to model time steps. These initial conditions were g, the planet's mass, the spaceship's mass, and delta t. The spaceship and the planet were known to be the system, while the surroundings were everything else. The mass of the black hole were found in part 1 and used again in part 2 as substituted in variables. The maximum time that was running simulations was 10 minutes. Like the decomposition in part 1, the gravitational force exerted by the black hole and ship on the planet, as well as the planet and the black hole and the ship, were summed individually. I used an equivalent form of the unit position vector to find the total gravitational force exerted. Worth noting is the incorporation of both the position and the velocity update formulas to determine the ship's location. Shown to the right are the translated formulas grouped by proximity. The results of part 2 are shown here, with the ship's trajectory deflected by the black hole in a slingshot manner without actually crashing into it. With trial and error, adjustments were made to avoid crashing into it, and the planet and the initial velocity were shown. The signs of the x and y components suggest that the spaceship was moving left and upwards, with magenta denoting the spaceship and cyan denoting the planet. The shortest distance was about a few percent of the radius of the planet's orbit around the black hole, and this escape speed is just one of potentially many that allows the spaceship to fly by. This experiment was entirely computational. Theoretical and systematic errors may have been introduced. The use of non-relativistic momentum may have contributed to inaccuracy in part 2, and the velocity of the spaceship was approaching the speed of light. Addressing what if the lab's experiment, the net force and its parallel and perpendicular components are different from the rate of change in momentum in those same components. The approximation was accurate for small iterations of delta p, but may be deviated if there are additional uncertainties in the experiment. To answer what does it mean for part 2, to enter an orbit around the black hole for prolonged observation, the x and y components of the initial velocity would have to be smaller and larger than those calculated for the flyby, respectively. The calculation of the full orbit shown here was finished after approximately 180 minutes. In short, these data have demonstrated that computational or in silico models are powerful tools that can simulate real-world conditions with various parameters and find unknown values. Thanks for watching.